Space is often depicted as a serene, empty void, a silent stage where stars drift by in the distance. But physically, space is a violent environment, and one of its most insidious weapons is temperature. While we tend to focus on the heat of re-entry or the radiation of solar flares, the creeping, absolute cold of the cosmos is arguably a more difficult engineering challenge. In the shadow of Earth, or on the surface of icy moons like Jupiter's Europa, temperatures plunge to hundreds of degrees below zero. At these cryogenic depths, the materials we have spent a century perfecting, the polymers, rubbers, and alloys that hold our spacecraft together, undergo a catastrophic transformation. They lose their flexibility. They become as brittle as glass. A single microfracture, invisible to the naked eye, can propagate instantly, shattering a hull or breaching a seal. We have seen this physics play out in tragedy. The 1986 Space Shuttle Challenger disaster was, at its core, a failure of material science in the cold. A simple rubber O-ring, stiffened by a frigid Florida morning, failed to expand and seal. That was just on Earth. In deep space, where temperatures dip to -270 degrees Celsius, the challenge is exponentially harder. For decades, engineers have dreamed of self-healing materials that could repair these inevitable cracks. We have self-healing plastics on Earth. Think of phone screen protectors that smooth out scratches over time, but there has always been a catch. Traditional self-healing requires heat. It relies on a process called diffusion, where molecules wiggle and flow to patch a gap. But in the vacuum of space, diffusion is dead. At cryogenic temperatures, molecular motion grinds to a halt. A self-healing polymer in space is just a frozen, broken piece of plastic. This was the accepted dogma of material science. You cannot heal without heat. But in early 2026, a team of researchers from NYU Abu Dhabi and Jilin University shattered this rule. They unveiled a new class of smart organic crystals capable of self-repairing at -196 degrees Celsius, the boiling point of liquid nitrogen. This breakthrough, centered on a material known technically as PBDPA, promises to usher in a new era of immortal spacecraft components. To understand why this is such a massive leap, we need to talk about the crystal paradox. To understand the magnitude of this discovery, we must first unlearn a basic intuition we have about solids. We typically divide materials into two camps. In one camp, you have the hard and brittle stuff, like diamonds, salt crystals, or glass. They are strong, but if you break them, they stay broken. In the other camp, you have the soft and healing stuff, like skin, rubber, or certain gels. These can repair themselves because their molecules are disordered and mobile. The breakthrough with PBDPA is that it bridges these two worlds. It is a crystal, defined by a rigid, perfect lattice of atoms, yet it heals. And remarkably, it heals better when it is cold. Professor Pants Naumov and his colleagues discovered that PBDPA, a small orange-colored organic molecule, defies the need for heat. The secret lies not in the random wiggling of molecules, which is diffusion, but in electrostatics. The PBDPA molecules are dipolar. This means they have a distinct positive end and a negative end, acting like tiny, powerful magnets locked in a grid. Imagine breaking a bar magnet. If you bring the pieces back together, they don't just sit there. They snap into place with a satisfying click, held by invisible magnetic fields. PBDPA works on a similar principle, but at the molecular level. When the crystal fractures, the exposed surfaces bristle with unrequited electrical charges. Even at -196 degrees Celsius, where physical movement is impossible, these electric fields remain active. As soon as the fractured faces are pressed back together, perhaps by the natural thermal contraction of a spacecraft hull, the dipole-dipole interactions zip the crystal back together. The result is a seamless repair. In testing, the healed crystals recovered their full mechanical strength and, crucially, their optical transparency. They could transmit light just as well as a pristine crystal, a feat that is nearly impossible with traditional glued or patched materials. This leads us to the second half of this revolution, where we make these materials. While the discovery of PBDPA on Earth is revolutionary, its true potential may only be unlocked in orbit. This brings us to the concept of microgravity manufacturing. For over 3 decades, from the Space Shuttle to the International Space Station, astronauts have been growing crystals in space. This isn't just a hobby, it's a critical industrial process. On Earth, gravity acts like a bully in the petri dish. As crystals grow from a solution, gravity causes convection currents. Heavier fluid sinks, lighter fluid rises. This turbulence creates defects, twists, and imperfections in the crystal lattice. However, in the weightlessness of the ISS, these currents vanish. Crystals grow in a purely diffusive environment, organizing themselves atom by atom with mathematical precision. The result is crystals that are larger, purer, and more structurally perfect than anything we can produce on the ground. For a material like PBDPA, perfection is power. Since its self-healing mechanism relies on the precise alignment of positive and negative poles, any defect in the crystal structure acts as a barrier to healing. A space-grown PBDPA crystal would theoretically possess a near-perfect lattice alignment, maximizing the dipole forces. NASA and commercial space partners are already looking at in-space production applications. We are moving from an era where we bring materials to space, to an era where we build materials in space, for space. Imagine a factory module on the upcoming Axiom station, quietly growing vats of self-healing organic crystals. These aren't just raw materials. They are the spare parts for the station itself. The implications of cryogenic regeneration extend far beyond simply patching cracks. This technology enables entirely new concepts in mission architecture. Let's look at 4 specific applications that change the game. First, we have self-aligning optical sensors. Deep space probes like the James Webb Space Telescope rely on mirrors and lenses that must maintain alignment to within a fraction of a nanometer. The cold of space warps and cracks these delicate instruments. An optical sensor made of PBDPA-coated crystals could suffer a microfracture from a micrometeoroid impact or thermal stress and simply blink it away. Because the healing restores 99% of optical transparency, the telescope would effectively repair its own vision without human intervention. Second, consider the Europa lander. NASA's plans to explore Europa, the icy moon of Jupiter, involve landing on a surface that is -160°C. A traditional rover's wheels and joints would face immense stress at those temperatures. Cryogenic self-healing crystals could be integrated into the composite materials of the rover's chassis. If the landing impact cracks a strut, the extreme cold, usually the enemy, would actually preserve the dipole alignment, allowing the rover to heal its leg by simply compressing the fracture. Third, and perhaps most vital for human survival, are living spacesuit visors. A crack in a spacesuit visor is a death sentence. Current polycarbonates are strong but degrade under UV radiation and thermal cycling. A laminated layer of organic self-healing crystal could serve as a failsafe. If a piece of debris strikes the visor, the crystal layer would maintain structural integrity, snapping back together to prevent a catastrophic decompression. Finally, we have data storage and electronics. Organic crystals are also semiconductors. PBDPA has shown promise not just as a structural material but as an electronic one. We could envision organic electronics that can survive the harsh radiation and cold of space better than silicon. If a cosmic ray disrupts the crystal lattice of a memory chip, the material's natural electrostatic forces could help realign the structure, preserving the data stored within. The discovery of cryogenic regeneration marks a philosophical shift in how we design for space. For 60 years, we have fought against the environment. We built heavy, armored shells to resist the cold. We built redundant systems because we assumed things would break and stay broken. PBDPA teaches us to work with the environment. It uses the cold to stabilize the crystal and uses the vacuum to prevent chemical degradation. It suggests a future where spacecraft are not static metal cans, but dynamic, organic-inorganic hybrids that respond to injury like living things. As we look toward the Moon, Mars, and the icy giants beyond, we will need machines that are as resilient as the explorers who command them. We are entering the age of the regenerative spacecraft, vessels that heal, endure, and survive the long, frozen dark. The crystals growing in the labs of NYU Abu Dhabi and soon, perhaps, in the microgravity racks of the ISS, are the first seeds of this new frontier.